Hi everybody, welcome to the Computability and Complexity course. The goal of this course is to give you a correct and complete exam preparation guideline, which is easy to understand, such that you will be exam ready in the fastest way possible. Now, the easy to understand part may feel really skeptical to most of you. And why is that? Because this course has a bit of a bad reputation, right? But I believe if we can understand the reason behind its difficulties, we can conquer them effectively. So why is this course hard? First of all, it's a formal theory course. This means it's abstract. It has a lot of definitions, a lot of problems to discuss, also proof techniques. In addition to all that, there is also this theory and practice gap. Because of the fact that it's a theory course, you may find it hard to make this theory applicable. Additionally, it's also a lot in general. There's a lot of topics to cover under complexity and computability. Because of all these reasons, this course leaves students feeling like this. But don't worry, because I've got you. So let me explain to you how I will approach these. This course will consist of 3 parts: fundamentals, computability theory, and complexity theory. Now, remember that I said that it's abstract. And when I'm talking about definitions or some problems or some proof techniques, if I see something is a bit hard to understand or something is a bit abstract, then I will always have this intuition box consisting of the same information, but in the easiest way possible, such that it will be really easy to understand. Now, fundamentals part will be all about what you need to know in order to understand the rest of it. For example, what is a Turing machine? Then follows the computability theory with the definitions, problems, and proof techniques, meaning proof recipes, but also some examples that we will solve together. Then follows the complexity theory with definitions, problems, and proof techniques as well. We will also have solved examples together such that everything is applicable at the very end for you. Now, what exactly are these definitions, problems, and proof techniques for each part? For computability theory, we will talk about what decidability and undecidability is, what is recursively enumerable, what is Turing complete, what are these Gödel numbers as representations. For the problems part, we will have the diagonal language, the complement of it, the halting problem and its variants, the PCP problem, MPCP, loop, while, and many others. Regarding the proof techniques, we will have the subroutine technique, Rice theorem, and the reduction technique. As I said, we will have a recipe and bunch of exercises solved together so that it sticks and you can really solve it yourselves as well. Now for the complexity theory, we have a bunch of complexity class definitions. P, NP, NP hard, NP complete, strongly NP hard, co-NP, NP intermediate. Then we have P space and NP space. Right, a lot. But don't worry, I will break it down in the easiest way possible, as I said. We will also have a lot of problems to discuss. The set problem, tree set problem, clique, independence set, vertex cover, Hamiltonian cycle, TCP, coloring, X cover, subset sum, partition, knapsack, bin packing, and a bunch of others, really, that couldn't even fit here. But if you can understand the proof techniques well, know that it's applicable to any of problems that you may come across. So we will have mainly 3 proof techniques. First of all, a recipe about showing a problem is in P. Then we have P reduction, and we also have a recipe for NP completeness. For all of these, we will have a bunch of exercises to solve together. Right. As I said, we will have the fundamentals, then computability theory, and complexity theory. I am ready. If you're ready as well, let's dive right into it.